of land has been already burned in California, and it's not getting better, it's getting worse. Drought is increasing, earthquakes are increasing, and yet at the same time, so many households are in harm's way, are sheltering in place from the pandemic. We call our community partners that are on the front lines the most vulnerable communities. These are the communities that are the first to get hit by an event and take the longest to recover from the consequences of climate change. These are communities that need support, and we are here in partnership to support these communities through this program and other work we're doing. We also know that many of these communities have faced a legacy of disinvestment and a legacy of challenges that has led to where the vulnerabilities are right now. Communities that have faced redlining or lack of investment for maintenance of infrastructure face incredible risk and vulnerability as we go into a changing climate. Next slide, please. And so our Keep Safe Guide is built with over 150 experts from across Puerto Rico to understand and identify the most important strategies that you must consider as you build and design and operate homes. These guides are available to you. They're free, they're online, they're available in print, and they provide guidance on what the strategies are, how to implement these strategies, and how to build housing that's safe. Next slide, please. The main sections of our book mirror the training series that we were providing to you. We started with Ada Monzon many weeks ago to talk about the introduction to climate risk. How do you identify your climate risk? What should you look out for? And then we moved to the site. How do you fortify your site with green and gray infrastructure? How do you make sure the site is able to deal with drought or flooding or earthquakes? Then we moved to protection. And protection is where we look at the structure, the homes, the roofs, the windows and the anchorage. Then we move to energy, where we look at how do we back up our energy? How do we provide energy solutions that are sustainable and efficient? Then we move to water. What kind of water systems should we have in place to make sure there's enough potable water on site? How do we deal with septic waste? How do we deal with stormwater and potable water containment and catchment? Then we moved to last week, community resiliency. And what does it look like to build a community resiliency hub? What are the components of that? How do we ensure that communities are connected? And today I'm so honored to have Fernando Abruña speak with us about passive habitability. And this is about how do we design and build homes that can exist without electricity. I wanted to mention that currently throughout Puerto Rico, Vivienda, the Department of Housing is undergoing public input for the mitigation planning that's occurring. This mitigation planning will inform over $8 billion of funding that will go into resiliency of housing and of Puerto Rico. So it's really important that you pay attention to this. And if you're in Puerto Rico and want to weigh in, the sessions are going on throughout the week. This is a chance for you to say, we want to keep our housing safe. We want resiliency to be built in here to the mitigation planning, and they are very responsive. And next week, the Secretary of Housing will be with us to provide us with an update on what's going on. Next slide. And so the purpose of these series is to understand critical actions and strategies to increase resiliency of housing, to identify best practices and models in housing and community resiliency, and to create a virtual community with all of you to get the information out, to share, to have lessons learned, and ultimately implement these strategies. Next slide. Today, we're going to talk about the major strategies that relate to passive habitability, orientation of homes, providing cool roofs, shading the home, enhancing windows, choosing thermally efficient materials, and building to code. Next slide. Today, we're going to understand ways of reducing heat gain, increasing ventilation, controlling moisture and mold, benefiting from natural light, and then also understanding the concepts of grid stability and instability. All of you on the call will understand critical actions you can take to increase the resiliency of your building design, construction, and operations. Next slide. So before we go into the question of passive habitability, I want to spend a minute or two just reflecting on what the grid is in Puerto Rico and why we should be thinking about building housing that can survive without energy. Puerto Rico's electricity, as many of you know, and in many of your communities, you have similar utilities, is supplied by the Puerto Rico Electrical Power Authority, or PREPA. And this is a government agency that owns the electrical transmission and distribution systems for the mainland. Vieques and Culebra, which are two island communities off of Puerto Rico. So this provides 80% of the electricity generating capacity throughout the island. The power distribution is operated and maintained by PREPA, as well as the electrical generation. The majority of electrical generation comes from 40% petroleum fueled, coal fuels, 18% of generation as of 2019, with renewables at about 3%. There's a few wind farms across the island that provide several 101 megawatts of generation, but the grid itself is still mainly fed by petroleum. So this is important to consider. It's also important to consider, next slide, please, that the distribution systems are vulnerable to wind. And this is a picture from a distribution system, a major distribution system out of San Juan that was destroyed after Maria. These distribution systems are vulnerable because their lines are above ground, vulnerable to wind risk, and the land and the site is vulnerable to, in some cases in the south, liquefaction from earthquakes, which is when the ground dissolves, or the lines are vulnerable to a variety of other hazards, such as rain or flooding, which can topple the footings of these distribution systems as well as the systems themselves. And so this is the major problem we're dealing with, which is a lot of homes lose power, and that power is not put on quickly because the distribution systems are hard to re-erect as well as maintain. Next slide. Over the years, the budget for maintenance, such as clearing trees to help ensure the distribution is in place near power lines, has diminished. In 2014, there was $202 million for this maintenance, which was a reduction of $50 million from 2007. What does this mean? Next slide. This means that when the distribution lines go down because they're not maintained, the power goes out. And when the power goes out, the households are left in the dark. Next slide. How can we learn from our ancestors, from the past, about adapting to a future where these power lines are not stable? They will continue to go down. The grid will continue to fail because it is a very difficult system to maintain and operate, particularly with less funds coming in. So today's conversation is critical. Next slide. Because we have someone with us, Dr. Abruña, who is not only a great colleague of ours and friend of our program, he is in many ways considered the father of green in Puerto Rico. He had the foresight and the vision to bring these concepts to Puerto Rico at a time when no one was talking about green. The connection and the dependency on oil and mechanical systems was at its height. And so Dr. Abruña has been working fearlessly for years to champion the sustainability principles and principles of our ancients, to bring back natural ventilation, to bring back natural lighting. He has been one of the most incredible partners to work with on our book, which is why we wanted to dedicate this session to him. He's the founding past president of the U.S. Green Building Council, Caribbean chapter, a publicly recognized authority in sustainable design, and is in charge of his own architectural design practice. You'll hear more about that today. Next slide. And I would be remiss without thanking our incredible language translators from OGMA, which is a woman-owned translation firm based in San Juan, Puerto Rico. And so Selena and Nicole are with us today, simultaneously translating. Next slide. If you are attending today and you want credits for this by the AIA United States, you can get those credits. If you'd like credits through the Colegio de Arquitectos y Arquitectos Paisajistas, you can get those as well, or PDH credits, or we'll provide you with a certificate of attendance. All you have to do is sign up, and we'll send you that after this this call. Please feel free to ask questions. Use the chat. We're here as a community to come together to listen to Dr. Abruña and to talk about this most important concept of what is passive habitability. Dr. Abruña, turning over to you.
Okay, everyone. Glad to be here. Let's just jump into it because we have plenty of things to say and talk about. And I'll just share my screen now, and I hope you're able to see the PowerPoint presentation. Well, first of all, I'd like to give my gratitude to Lori, who has the energy of a Cat 5 hurricane. She's always moving real quick and making us all aware that we need to move. And all the previous lecturers and the Keep Safe team that have paved the way for today's presentation. So at the risk of sounding repetitive, download the Keep Safe book, read the Keep Safe book, implement the strategies in the Keep Safe book, and become sustainable and resilient. The guide is it's a magnificent, it's a great resource that everyone can use. It was done and designed so that everyone can make informed decisions without being a technical person. So if you're not an architect, or if you're not an engineer, or you're not a resilient expert, you can dig into the book and get all that information. So I'll talk a little bit about our office. Ours is a very small office. We have 5 consultants that we have partnered with for most of our professional life, which is now 43 years young. We don't actively look for work, okay? So our work finds us passively because what we actually do, and this I learned from Bucky Fuller, with whom I did my doctorate. I just don't want to convince people to do sustainable or resilient projects with us. I do presentations like this one, I write books about it, and so people learn about our work through our presentations and our books. So when a client walks through that entrance door at our office, they're already convinced that sustainability and resiliency are the way to go. So 40 years ago, it was a hard sell, but now since the resiliency and sustainability movement has matured, it's an easy sell for us. So we don't even look for work. It just gets to us. Finally, and this may sound a bit self-serving and immodest, we don't design for awards in mind. Most of them have come from environmental institutions anyway. But if we do get an architectural award, we know the profession is moving in the right direction. Sorry about that. So this is the main topic that we'll be talking about, passive habitability. and passive survivability. When we talk about habitability and survivability, they're both very much related. Passive habitability is the capacity of a building to keep working for its inhabitants, even in the absence of life support utilities like electricity and water supply, and even the storm water, black water, etc. So the idea of passive habitability is for us to design a building that will ensure the use of the forces of nature, so that when we install the utility systems, this will be as small and efficient as they can be. So if I were to design a house with the right orientation, with the right materials, with the right windows, most probably it'll be a cooler, for our tropical environment, it will be a cooler environment, and whatever energy I'll spend in cooling that house for air conditioning, for example, it'll be less. And I'll give you some examples as we move along with the presentation. So if you use the forces of nature as your design toolbox, you will find simple solutions to complex problems. And this is our office mantra: be efficient to such an extreme as to be able to do almost everything with almost nothing. So we have that posted everywhere in our office. So the people who work with us are always invaded by this aphorism that we use often. So if we do sustainable design, in reality, the world is our client. It's not the guy or the institution that signs the check. If we engage in sustainability and resilience as our design goals, the world is really our client. Climate change is a world problem with no frontiers, and our design practice needs to do the same. Most of the emails and messages I send, I usually end them with this aphorism: if it's only beautiful, make it also sustainable. If it's only sustainable, make it also beautiful. Because if it's beautiful, you will also want to maintain it. And one thing that we learned after Maria is that maintenance is such a core concept when we talk about sustainability and resilience. I remember the school we did in Culebra, the very first eco school in Puerto Rico. It had triple redundancy in the electrical system, and all of them failed. The grid failed, the photovoltaic system failed, and the electric generator failed because no maintenance was given to any of those systems. So maintenance is a core concept when we talk about sustainability and resiliency. The basic principles that I will speak about are listed here. Cool air sinking. They're very basic. It's very basic information that you probably learn in your elementary school and maybe even in high school. Cool air sinks, hot air rises, water ponding increases humidity in the air. Humidity brings pathogen growth, mold, and mosquitoes. Lower humidity brings comfort in the tropics. So that's one of our major concerns when we do natural ventilation: lower the humidity levels. Sun versus shade and shadow, wind versus breeze and comfort, and among other things, and above all other things, be fair with all involved: people, animals, plants, nature. Okay, so let the behavior of materials you select and the properties of forms that you give to your building and the forces of nature like wind, rain, sun do the work for the building. That's what we try to do when we do passive design. So let's get into how we deal with the sun. If you look at the picture I'm showing now, I hope you can see my cursor. If it's a squarish building, there's not much you can do about orientation because you have the same area facing all different orientations. If you do have a rectangular building, which is probably the best shape for tropical climates like ours, you will, depending on how you orient the building, you will have more radiation coming into the building or less radiation. So here we can see that the larger facades are facing north and south. And since the sun comes out from the east and sets in the west, we have smaller facades on those orientations. So this building versus the one on the right, which has the smaller facade areas to the north and the south, this one here on the right will consume and will require more energy than the one on the left, just because of the orientation factor. So it's very important for us to be aware of how we place that building in our site. Since the sun moves on a higher altitude during the year, in the summer, the angle, and I'll show you a picture to better understand this. The angle will make it almost a requirement to have overhangs to protect us from that sun. But in the south, the altitude angle is much more lower, and that happens during the winter. And during the other parts of the year, the sun comes out in the east and sets in the west. So typically what you want to do when you want to protect your building, you want to have vertical shading devices on the east and west orientations and overhangs on the north and south. If it's another orientation, say it's like northeast or northwest or southeast, southwest, then you use a combination of both. here you can better see the relationship between the winter sun and the summer sun. Okay, so it's high, the angle is very high. So with a shorter overhang, you can protect that wall. And in the winter, with a longer overhang, you can also protect that wall. In the east and west, we will be using then the vertical shading devices. You can also use vegetation. You can use a vegetation hedge, a planting hedge, or a tree to do basically what we accomplish with overhangs and vertical shading devices. Let's do a quick exercise here. Let's take the following scenario. This is a typical urban lot with typical urban development with 9 lots. North is facing this way, and we are to locate a house with an adjoining garage, no overhangs, and just 1 tree. If I were the developer, this is most probably how I would end up doing it, okay? With the larger facade facing the street so that the house looks more regal, more important than if I were to locate those houses with the shorter facade to the front, to the street front. But if you look at them closely and you use your sustainability acumen, you will notice that these 3 houses will behave much better than this other here, just because of the orientation factor, okay? North, south, east, west. But of the 3 houses on top, the one on the right will be even better because the garage will be protecting the west facade of the house, and it will act as a buffer for that heat that penetrates the house in the afternoon. So in general terms, you wanna locate those spaces that you use in the morning on the west side of your house, and those that you use in the afternoon in the east, because the sun will be in the opposite side where you'll be using your house. So this is just an example, right? Like the garage on the west to protect the dorms, and the storage area on the east to protect another dormitory. So this is just a general idea of how to have that into your mental picture of how you want to order the interior spaces of your house. You can also remodel. Say you move to an existing house and you want to improve the thermal comfort inside that house. One possibility is to rearrange those interior spaces. Again, these 2 bedrooms are on the west side, and typically you go into your bedroom after in the evening, so those will probably be very hot in the afternoon. So you can relocate those to your advantage, as shown here. Okay, again, a garage will be serving as a buffer zone, and the same thing here. And the bedrooms now will be located on the right, on the east facing side of the house, and that will allow us, when we come back in the afternoon to use those bedrooms, they will be cooler than if they were located in the west. And these are some other elements that we just spoke about, the contextual elements, the sun, the tree, and the shadow that it casts upon the building. If it were a mountain, it would do just about the same. So that sighting is very, very important. But actually, of all the decisions that I as an architect make, sighting is probably the most important one, even more important than the architecture itself. Sighting is just absolutely essential and a core issue when we work with sustainable and resiliency tools as our design, for our design solutions. The same thing with convective currents, like the one shown in this slide, can affect local and regional wind patterns and direction as a result of where green and gray infrastructure are located. Here, for example, this dark concrete surface will absorb more heat and will make that heat flow upwards. As it does, it will suction cooler air coming from the shade cast by those trees into the interior space. So in general terms, the way wind moves regionally in the coast where we have the ocean front, it will behave in one way. In the mountains, it will behave similar to what I was showing here. We have convective currents in ocean with the ocean breeze during the day. Since the land is hotter during the day, that same thing happens, just as I explained in the previous slide. Hot air rises, cool air comes in through the house. When the evening falls, both temperatures, land temperature and sea temperatures, cancel each other, and that's where we have a lull and no wind goes anywhere. There's no wind at all, no breeze, and that's when mosquitoes get you. So, and that happens between 6 in the afternoon and maybe 7:30 and 8 p.m. Right after that, we get again a temperature differential, and again we'll get our breezes coming from land into the sea. The same thing happens in terms of your location with relation to the topography. Right here, you see the topography, how the house is located in the lower part of that topography, and how humidity collects there. So if you want to prevent mold, you get out from that area and you move up here where you won't have the humidity that you would typically have down here. So it's very important for us to have a compass. This is a very important tool to have at all times. On the left, you have an active, and I'm using this as an example to give you a sense of what passive systems are about. That cell phone needs electricity to work as a compass. The other one, the passive compass, works with Earth's magnetic forces. So with or without electricity, this compass will always be working, but this one will not if you don't have electricity. So that's what we mean by passive design. Use the natural forces of nature, what nature gives us: wind, topography, trees, water, rain, sun, as our major resources for the design. Here we can see building shape in terms of photovoltaic radiation collection to generate electricity. If you have a concrete house, 15 degrees will be great, and 15 degrees is an angle that many architects use because it just sort of looks nice. But it works just fine to locate your photovoltaic panels looking to the south. If it's a wooden house, it's the worst angle you could have because it begins to take the shape of an airfoil, a wing, and wings are designed to lift off. So if your house has a 15 degree, your wooden house has a 15 degree or lower slope, it'll act as the foil of an airplane, and when you get hurricane force winds, the roof will be blown away. The same thing with the sun. If you have a rectangular building or a dome building or a gabled or hip roof building, the way the sun moves through that house will be different. You know, in this case, for example, you will get heat on this side of the roof in the morning, and this side on the west in the afternoon. And in terms of rain, if you were to collect rain, these two shapes will require two gutters in order to collect all the water. Here you would only need one, and the slope will be in such a way that it will let whatever heat is collected inside the building naturally out the building. If we talk about the wind, common sense tells you that having windows on opposite sides of a room is helpful, but that it's not enough. Knowing where the wind blows from is absolutely essential for the wise location of windows, as seen in the next slide. There you go. This one is the windows were located to coincide with the prevalent wind direction. This one was not, and look at the difference. Both would have what we would normally call the potential for cross ventilation. This one does, but this one doesn't, because we didn't take into consideration the main orientation of that wind. We can fix that. In this case, we have a building with two windows, but the wind coming is parallel to those windows, so we don't have any wind going through the building. In order to, if we want to fix that, we can use a berm or a hedge or even a freestanding wall, and the wind pressures will collect in such a way that it will force the wind to go through the house, even if the windows are not perpendicular to that wind force. We also have to be aware that when we plant trees close or hedges close to the house, the wind speed is reduced significantly. Okay, so that's one thing that you have to take into account. Keep your distance in order not to interrupt those breezes into the house. Here, this is a very important slide. The next couple of slides are very, very important. And there's one that's absolutely important, and it deals with how the wind behaves inside the building. If you look at it closely, the wind here is moving up into the space, and here it's moving even higher into the space, almost to the ceiling. That behavior is determined by the wall area that you have facing the wind. So here we have more area under the window than we do above. So the force component will force the air in this way. Here, when we put in an overhang, whatever pressure points we had here are canceled, and the only vector forces that we'll be having will be coming from below, and that forces the wind to the upper part of the house. What we do want is for the wind to go through our bodies so that we can shed heat into the wind. Okay, we can separate the overhangs and reestablish the same wind pattern that we had before. If we use a shelf or a bench, look how different the wind pattern inside turns. And this is like a more or less the same thing, except that it's more, I believe it's more clear because of the symbols that we put here. There's more pressure here than there's there because there's more area here than here, and that forces the air down. Here we have an overhang, so this is canceled. This could be a second floor or a very large parapet, but the lower force, the lower area will force the wind above. You can have a second floor, or you can have no overhang, and since this area will be bigger, vector pressures will be higher here than they will be here, and the wind will be forced down into your body, but that's what we want. Ventilation by convection, also called the stack effect, is good for health ventilation, but typically not good enough for comfort ventilation. You need a certain speed, typically between 5 and 8 miles per hour, to get a comfortable ventilation effect. The stack effect will move the air, but it will be very slow, and you will get some cooler air from the lower parts of the building, but still not enough to make you evaporate your sweat. So if I were to simplify all that we have explained so far, this is a summary of that. North overhangs, short. If you want to protect yourself from the rain, it'll be longer. On the south, you want longer overhangs, and you want windows as big as you can so that the wind flows through your body. You can also use berms to protect against the heat load, and you can add an overhang and have the whole wall protected from radiation. If you use 8% of your roof area with skylights, that will provide you 100% of daylighting in a building. And the trick here is to maintain your width from window to a maximum of 30 feet. If you do a bigger area, then you will have some obscure or shaded areas in the center of the building. You could solve that with the use of skylights. And this is like a glossary of different possibilities for indoor daylighting: clear story windows, lighting shelves, flat skylight, pyramid or dome-shaped skylights, a monitor with an overhang protected skylights, directional skylights to the north and to the south, directional skylights only to the north, which is the best location because you will receive lots of light and very little radiation. So let's talk a little bit about iguanas. Iguanas are a big problem in Puerto Rico. There's more than 10 million of them here, and it's very difficult to control them because they don't have any natural predators. So they typically die when they try to cross the streets and the roads, and you see them being squashed by the cars. I had a problem at Casa Ausente, which I'll be showing you real soon. We tried many things. The one that worked the best was red pepper, believe it or not. I sprayed red pepper into their caves, and we got rid. At one time, we had 60 of them in the house. Mosquitoes typically need 10 to 14 days to develop in standing water, so it's also very important to dump that standing water. And we have to be careful with rain gardens, which are much talked about these days, in clay soils, and we have plenty of those here in Puerto Rico. During the rainy season, they could become breeding gardens for mosquitoes. You could use these solutions. You want to keep away from DEET, and you can use the natural way with no chemicals by using these plants. And you can also work with water, with electricity, with a pump, or you can use gravity and let it filter into the earth. These are very simple strategies. Pave the roads, trails with permeable gravel, stone instead of concrete. The light reflected by yellow, the color yellow, keeps away insects, making unnecessary the use of insecticides, toxic to your health. So we typically, on open outdoor spaces, we use yellow lamps that will keep the mosquitoes away without the use of toxic chemicals. The same thing with green. Forest green is a color that it's in its pigmentation has something that termites and polilla y comején don't like. So without using any chemicals, just because of the pigmentation of that particular color, that will protect the wood you paint that with. So passive survivability, if I were to make a summary of what we talked about, why depend on pumps if we have gravity? Why depend on lamps if we have daylight? And why depend on air conditioning if we have a breeze? So I'm gonna be showing you some case studies real quick. This is the UPR Decathlon House that we did in 2001. We got a second place in the sustainability and habitability competition. It's an elongated form, as we were talking. We have the photovoltaic panels facing south, many windows in the south. This was located in Washington, D.C. in the Washington Mall. So the conditions there are different from ours, but still the south facing windows need to be protected. So instead of having a long overhang, we have very many of them, but very short ones, and they do the same job. Here's how it looks with the shading devices and the photovoltaic panels, and how we assembled that house in Washington. Solaria, in Solaria we use thermal insulation everywhere. This is some shots of how we built that house. They're all core insulated concrete structural panels. The white stuff you see there is expanded polystyrene. And we built this in two or 3 days, and we spent about 2.5 weeks plastering it in, and in about a month and a half, we had a finished house that was based according to this sketch that you see here with the bedrooms. And this, again, we're using this as a buffering zone. The same thing here with the rainwater collection. That's how it looks. And you can see here how the building was shaped. The southern, this slope faces the south, so that the solar hot water heater collector and the photovoltaic panels are facing in the right direction. But there's also a slope coming into this corner, so that all the rain that falls into that roof is collected into this rainwater harvesting cistern, which works with a pump that pumps the water into the house. This is how it looks from the interior. We even published, as part of the house, a user's manual, which I believe all houses would need. You know, when you buy a computer, you get an instructions booklet. when you buy your refrigerator, it comes with instructions, but when you buy your house, you don't get that. So we believe this is a good instrument that needs to be used when we do design work. You want to let know the people you design for how the building works, how it behaves, if they're going to make changes, how to do those changes so that they do the right thing at the right moment. EcoHab are two houses that we did for the HUD, for Housing and Urban Development, the home program through the municipality of San Juan, and they were certified as Energy Star homes and also LEED for Homes Gold. And this house is very interesting in the sense that it's a typical suburban lot. There's two houses. This is one of them. This is the elongated one. Is another one, and both of them have interior patios where we can have improve the daylighting. And this one here and this one here both have what we call transformable or transformable walls that can be pulled up or down in order to make those spaces react passively and make the transformation of them possible without any interior construction work or demolition work. So here you can see how that behaves. A bedroom could become a potential future office looking into an interior patio, or this interior patio could become a larger dining room with a skylight on top of that. And the same thing with the other house. The transformable walls allow you to have different bedroom configurations as the family grows and changes through the ages. So early on, this is more or less the interior arrangement, and as you get older, this would be the typical arrangement. We used precast core insulated structural concrete panels for this house and for these two houses, and this were assembled in 2 days, and the roof was poured in place, and it took us about 2 weeks to plaster the whole thing. But in about a month, we ended up with the house you're looking at. This is the bigger one, and the other one I'll show you some. We got a patent on that window that you see here, and I'll go real quick on how that works. It has an aluminum shelf, shading shelf, and 3 glass jalousies. So if you want to get natural ventilation and daylighting, you leave those open and you have your breezes go through and you have plenty of light coming through that glass. If it's really hot and you want to turn on your air conditioner, you leave the shading eaves open, but you close the glass jalousies so that you still have the benefit of natural daylighting, but no air conditioning. The air condition will not go out through the building. And in case of a storm or hurricane, you overlap the aluminum shelf on top of the glass jalousies, and it becomes a storm shutter. That's how it looks. And these are some shots of the interior of those spaces. Look at how, and these are not retouched photographs. These are real photographs taken at the site with the use of the window I was just talking about and the use of interior patios. How nice the lighting conditions are there. So no lights there. This is all natural daylight. This is the other house, and you can see here what I meant by transformable walls. We're looking now from the kitchen and dining room through an interior patio into a bedroom, but you can close those to get some privacy. Here they're all collected, they're all collapsed up here, so the whole house opens up to natural ventilation. We have a 15,000 BTU unit that cools the whole house. It's close to 1,000 square feet. In Puerto Rico, we typically use 12,000 to 15,000 BTUs per room. This whole house is cooled with just one mini split unit because we're using plenty of insulating material, both in walls and on the roof. This is one of the nicer shots, I believe, that shows you looking from one interior patio into the other, and the single air conditioning unit, that the air is distributed with the use of ceiling fans. We also have, our photovoltaic system, a very small one. And we also designed a cover for those interior patios in case a hurricane comes up. You can shut those down and you can still have the benefit of restoring those interior patios once the storm is over. The House of the Horizon is a house that we finished in 2016, just before Hurricane Maria. And it's a very simple house. It's just a very, similar to the examples that I was giving to you. This would be the bedroom area, living, and a sofa bed that allows the owners to have like a second bedroom, kitchen and dining, and the bathroom with a composting toilet that uses no water. And this is how it looks. It's very open. It's like a big balcony looking into the landscape. So there's no need for air conditioning, although this is in Lajas where it gets quite hot. It's a very dry environment compared to the northern coast here in Puerto Rico. So the owner asked us to install an air conditioner, which we were not going to be able to put it to work with the small photovoltaic system that we installed. So what we ended up doing was, I'm just moving real quick so that you can have a sense of how this works. We installed, he's a anesthesiologist, a medical doctor. We convinced him to use what he's used to do with his patients, and close them with a curtain so that the air conditioner only needs to cool the area of that bed instead of the whole bedroom. Again, here are patented windows in order to get some shade. And we even installed what we call included as part of the design, what we call a lunar terrace with the lunar lamp that you see here. That lunar lamp is comprised of a mandala with white stones that shine really nice when you have a full moon. But when you have a new moon, there's no moon at night in those days, then this concentric circle here collects energy from the sun, and at night it glows. So it's a lamp that behaves differently when you have a full moon and when you have a new moon. So it's all passive. There's no switches, no electricity. It just works with natural night lighting, which we're not used to talk about. We typically talk about day lighting, but here we're using the forces of nature, again, the beauty of the moon as the protagonist of that solution. Ecovito is a very small, very, very, very tiny house. This might be even a nano house, but we also use lots of insulation material. Again, this would be a lunar lamp, very simple. This whole house runs with just one photovoltaic panel. The coquille was done with the students of the Sustainability Studio while I was a professor there, and the students built this themselves with a passive wall that opens up and becomes a pergola. This measures 8 feet by 12 feet, has a mezzanine with a bedroom. We collect water. There's a small photovoltaic system there that runs. It even has a composting toilet. There you have the small photovoltaic system. Rainwater is collected here and goes into the bathroom. And this is the house that we're working on now. We're almost done with these houses. We should be finished by the end of this month or by the beginning of next. And it's also a very simple solution with the long facades facing south and north. The north side is this one here. That's why we place the pergola on the north side, because it will get plenty of daylight with little heat radiation from the sun. This is how it looks from the front facade. Very, very simple. We have triple redundancy in the water systems. We have the utility water from Prasa. We have a Prasa-fed rooftop cistern and a rainwater harvesting system that works by gravity.
Dr. Abruña, we're
yes.
about 7 minutes left of our session.
Great. I'm almost done. This is how it's looking now. we hope to have this done very soon. This is the final project I will be showing. This is the Absent House. Here, this one, we spent the 45 days here after Hurricane Maria. And if you look at this house, it's sort of a strange house. I'll be showing to you, but just want to make you aware that this is a tower that it's inside an interior patio. And besides having a rooftop mounted and solar powered with this photovoltaic panel here from a river that crosses the house, water collected there is it's moved through a pumping system down below this bridge through the use of solar energy, and we pump it up and then we let it fall by gravity. But after Hurricane Maria blew away this photovoltaic panel, so we ended up with no electricity to pump up the water. But we do have this gravity rainwater cisterns that saved us. That's how it looks from above. We have some windows here, and this is mostly walls with very tall windows. So when we close the windows on this side, this becomes the bigger vector force that forces the wind through the interior patio. We call it the patio of the sun and the stars. And the air is forced into the living area. That's how it looks from above. That would be a drone photo. And this is how it looks from the interior. So if we close this window, all this area will force the wind through these windows, and you will notice that there's more area above the windows than below, so that the wind is always forced downwards into our bodies. We also use yellow lights in the open outdoor spaces so that we get rid of mosquitoes without the use of insecticide. We also have a green roof. We also
Dr. Abruña, some questions are coming in about the cost of some of these houses. There's a lot of interest in some of these systems, and I think one of the lessons I've learned today and through this period is that in new construction, there's an opportunity to design differently, yes, which saves you at the upfront of the construction. But could you speak to some of the costs related to these systems and how to implement those?
Yes, I will. Yes, I will. I'm just 2 slides away from the end of the presentation. These are plastic owls that are natural enemies of changos and blackbirds that infect the area. So without using any violent means, we got rid of them with just plastic owls. This is how it looks from the top. That's the river I was talking before. And this is the windows. Again, very important for the windows to go all the way down so that we get good ventilation. And this is how all those houses compare energy-wise. So maybe I'll leave this for later. I'll answer the question now. The house that you were looking at, let's say the house of the horizon, the one that opens up like as a balcony, that was $85,000, including the photovoltaic system and the rainwater harvesting and cisterns. Including also the lunar terrace. It's a miracle that we were able to build that house because it's way up in a mountain, very, very distant from roads. So we were lucky to have a contractor that was able to do the work up there. The Absent House was done in 1999 at a construction cost of $170,000, but it's like a very peculiar house because it's our house. So we designed it with some amenities that some people might not be supportive of, like the interior patio, the patio of the sun and the stars. In terms of architectural concepts, we thought that was real nice. But in any case, it's the cheapest house in the whole subdivision. Most of the houses there are run from between $450,000 to $650,000. Ours is $175,000. So it's like a pesebre of the subdivision. Um, the houses that we're building now for Caño Martin Peña victims of Hurricane Maria, the total cost will end up being $110,000 with the triple water system, the utility connection, the Prasa rooftop cistern connection, and the rainwater connection, the photovoltaic system. All those are included, and also the possibility of even a gas generator in case the photovoltaic system fails, the battery system fails. So in the other house, the Solaria, the one that had a sloped roof, that was $135,000. It's a 2-bedroom house, and it includes the photovoltaic system, the solar water heater, the rain catchment areas, the whole works. So in essence, I believe we've done a good job in terms of maintaining costs to a reasonable level. One thing that we learned right after Maria is that costs increased substantially, but quite a lot right after Maria. Our numbers were like 42% higher than the construction costs before Maria. And some friends of mine who work in FEMA were telling me at that time that their rule of thumb was 40% more than previous to Maria. So construction costs have gone up. So that makes it even more important to have passive solutions to building design so that they can save money while we use the building and we maintain it. So yes.
There's a couple of follow-up questions, which is, as the rebuilding occurs throughout Puerto Rico and in many island communities, is this a scalable model? And what would be your recommendation to ensure that this gets included in the rebuilding?
Absolutely. These are potential solutions that can be scaled up. For example, the house that we're building now for the victims of Hurricane Maria in Caño Martin Peña, we're working now on simpler and less technical solutions in order to reduce that cost. So we're hoping to reduce the cost to maybe $80,000–$85,000 for that house, including a solar emergency generator that runs with 2 photovoltaic panels and a small console that has 2 plugs, one for the refrigerator and the other one either for a microwave oven or some lights. So and they're all the houses that we've seen are earthquake resistant and hurricane resistant. Actually, the one in Lajas went through Hurricane Maria with no problems at all, and it just so happens that it stands in an earthquake fault. We didn't know about it. Nobody knew about it except after Maria. So we were fortunate enough to use very light material, insulating materials on the rooftop, and that really made a difference because it reduces the pendulum effect you have when you have concrete, solid concrete roofs that are more vulnerable to earthquake movements.
Dr. Abruña, we are sadly at time, but I'm hoping you can give us some advice or some final thoughts. This has been an incredible presentation, and we're all so grateful to you for your knowledge and your work in the world. Could you give us some final thoughts as we're going forward into a very volatile world, a very volatile climate?
Well, I want to close with the homework, which I'm showing in the presentation. I made the numbers. I figured out that in order to cancel our carbon footprint, Puerto Ricans have a 20-ton carbon footprint per year. And after Maria, we were left with an average of 500 trees per person, but we need 800 in order to counteract our carbon footprint. So if you want to help in reducing and making a carbon-free world, you need to plant 300 trees. You don't have to plant them all yourself. You can do some donations to private enterprises and to private organizations like the Puerto Rico Land Trust para la Naturaleza, who will plant those trees for you. So if we want to really do our work, we need to reduce that carbon footprint. And we can do that by planting 300 trees, each of us, and maintain them for the rest of our lives. In terms of the building design, it's always, the frame of mind that you need to live in one of these houses is that, again, nature offers us all the solutions. All we have to do is use them wisely.
Dr. Abruña, on behalf of the entire community from around the world, we are so thankful to you for today, for this lesson, and we will take this in the work going forward. We have a lot of work to do. So on behalf of all of us, thank you so much.
Thank you for the opportunity, Lori.
We have many questions coming in. We will try our best to work with Dr. Abruña and send you responses afterwards. Next week is our last session. The Secretary of Housing for Puerto Rico, the AIA, the Foundation for Puerto Rico Architecture, we're going to come together and talk about how to pay for this, how to pay for this incredible work, how to build it, who's on your team. You're always going to want to have Dr. Abruña on your team for sure. And Dr. Abruña, there's a lot of questions if we can get connections to you, so we'll make sure to send that afterwards. People are inspired by your work and your vision.
Okay.
Thank you all, and have a wonderful, safe week. We will speak next Thursday at 3 p.m. Until then, gracias muchísimo y adelante.
Muy bien, we did it on time. Great. Bye.